Welcome to Lecture 9 of Networks Friends, Money, and Bytes. In today's lecture, we will try to formulate and answer the question, can I really reach anyone in 6 steps? Now, this very famous 6 degrees of separation dates back many decades ago to the belief by sociologists that in social networks of various kinds, the distance between node pairs, between people, are actually quite short. But it was really codified by Milgram's experiment in 1969. Milgram asked people living in Omaha, Nebraska, to send a letter to a person living in the suburb of Boston. And there is the letter with name, address, and occupation. And that's it. No other information provided about this person. Now you probably think, yeah, I need to know the name and address. What about this occupation? Turns out that it is very helpful to know the occupation, because the rule of the experiment says that you cannot directly send the mail to the person in Boston suburb. You can only forward the mail to someone you know by first name. This is the definition of friend in Milgram's experiment. It is the definition of a link in this graph of social network. Okay, so you can only send it to somebody you know by first name. And then that person can further forward this letter to someone that she knows by the first name, until it reaches somebody who says, yeah, I know this person by first name. So it's a very interesting experiment, and altogether 296 people were asked to participate. It turns out that 217 of them actually sent out the letter, and out of those, 64 were completed, meaning that it reached the final destination. I think this is kind of a less than 30% completion rate. Well, indeed, we have to properly take into account in our statistical analysis what happened to the other 70% of the participants. But among these 64, you see something very interesting. Okay? And also in later replica of this experiment, such as by email in the 1990s, actually the completion rate was only 1.5%, even much lower. Okay, so if you look at this 65 list of letters that completed, and then count the number of hops it takes to reach this final destination, and then you look at the histogram of that list of numbers, you see actually it's quite a small number. The median length of the search chain, okay, this is a search chain, it's a chain of a social search, and the median length out of the 64 is only 6. And this is the magic number that leads to the so-called 6 degrees of separation. It says, roughly speaking, and as we'll see, very roughly speaking, in this entire social network we live in called the Earth, we can reach anyone in 6 steps or less. Well, first of all, rigorously speaking, this is only the median length. Okay, it is not the maximum length. They are very long chains. You can only say that, roughly speaking, it is quite unlikely that you can complete the search chain in a few number of steps. Okay, and the median is 6. There were so many extensions of this basic result that it would take actually a whole course to do nothing but to tabulate all those. For example, people have looked at the network of scientists, the network of movie actors and actresses. Here a link is a co-authorship relationship. Here is a co-starring relationship, and the list goes on and on. And to quantify the degrees of separation, and usually it's a pretty small number, even though the overall population is huge. And in 2011, November, it was reported that Facebook has a 4.74 degrees of separation, which is even smaller. So the question was raised, is Facebook flattening our social world further, bringing 6 degrees of separation down to less than 5? We'll later come back to this 4.74, but a first order question we have to raise is, what is the definition of a link on Facebook? As we mentioned last time, does that mean that you are in my friendship circle? Or does it mean that we have mutual wall posting? Or does it mean that we have a regular enough pattern of communication? Right. Later we'll come back to this 4.74 even further. So here's the histogram of the search chain in Milgram's experiment. Some chains were very short. Okay. 2 people actually so happen they know directly the final destination's person. And some chains took 10 steps. And you have to think that out of the 70% or so that did not even complete, some of them, at least some of them, were because the chain was so long, as it drags on, there's some chance of getting lost along the way. But the mean was 5.2, the median was 6. It turns out also to be the mode. And you wonder, what kind of chain does it look like? I was drawing a chain, but that was hardly a representative one. Here is a representative one. Here's a source, somebody living in Omaha, Nebraska. Here's the final destination in a Boston suburb, and usually it goes through some short range links. Okay. And here, by short range, I mean physical distance, short range. Later we'll also see there's also social distance of various kinds. And then it will usually use 1 or sometimes 2 so-called long-range links. In the physical sense, this can go, say, all the way to New York, for example. And then it will go through some further local chains before reaching the destination. This long-range link is a very interesting phenomenon. We'll soon discover that without these long-range links, it will be very difficult to have a small world. Now, how would you make sense out of this 6 degrees of separation? Is that surprising or not? On first thought, you might say, only 6 steps? I can reach anyone in 6 steps? Well, that's kind of surprising. I thought I have to take many more steps in this world of many people. So that's a surprising result. But then on second thought, you say, wait a minute. If I say I have only 20 friends, not a very popular person per se, but 20 friends, and each of them has also 20 friends, again, not hugely popular. Okay? I know if you look at Facebook as an example, a lot of people have thousands, tens of thousands of friends, even though most of them you really cannot qualify it as a link in Milgram's example, but still 20 is not a huge number. Dunbar's number is like 150, right? So assume that all these friends of mine only have 20 friends. Then in 6 steps, I can reach 20 to the power of 6, which is about 64 million people. So no wonder with 50% chance, 6 steps suffices, 6 steps or less, because even for these kind of configuration, I can already reach over 50 million people. So what's the big deal? Of course, 6 steps suffices. There's a lot of people that I can reach. So it's not surprising. And then on the third thought, you say, but hold on a second. There's a lot of overlap. Okay, here's me, and I got 20 friends, right? And I was thinking, it grows like a tree. Each of them got 20 friends. But the thing is that a lot of my friends' are also directly my own friends. There's a lot of duplication here. I cannot reach out to all another set of 20 new people from each of my friends. In fact, maybe all his friends are mutual friends too. So this tree just does not grow like what we just mentioned, 20 to the power 6. Then what? Well, we have to think about this phenomena. Try to model the homophily in a social network. It refers to the fact that a lot of times like-minded people, they tend to know each other. So my friends' friends tend to be my friends directly. And this is a specific notion of homophily called the transitivity in the social network. Remember, this transitivity refers to a property of a graph. It has nothing to do with the transitivity in voting theory that we talked about back in lecture 6. And one way to further quantify this notion of transitivity is to look at a specific case of that called triad closure. So as you can see from tri means a triangle, a three-way closure. And to quantify the amount of triad closures in a given graph through a single scalar number, the metric of clustering coefficient. So this quantifies triad closure, which is a special case of transitivity measure, which is one model of homophily in a social network. And that will explain this phenomena of a lot of overlaps. So whatever explanatory model we come up with for 6 degrees of separation, it can be this tree growing 20 to the power 6. It has to be something that also observe homophily or transitivity. So here is an example of a triad closure. We've got Alice, Bob, and Chris. Okay, so Chris knows two friends, Alice and Bob. Then we say if there is also a link, this blue line here, that Alice and Bob also know each other. Let's assume all links are bidirectional here. Okay. Then we say the triangle is closed with this link. This is what we call the triad closure. So we wonder, if I count all the connected triples, this is a connected triple, okay, in the graph I'm given, how many of them actually close the loop and forms a triad closure? Not all of them, but some of them. And it's believed that in human social networks there is a lot of closures. So I would like to basically count the number of closed triangles as a percentage of the number of connected triples, whether they are closed or not. Okay, it turns out this would not be exactly the metric we use the formula because it doesn't normalize to what we want, but it captures the essence of the idea. If this is a big number, then we say we indeed observe a lot of triad closures and therefore transitivity in social network. So our explanatory model, what we come up with as a model to explain the existence of short path, got to also observe a high clustering coefficient, something like this. So that remains a mystery at this point in the lecture. Okay, we'll later resolve it. But it is surprising. Now we see finally the first true surprise of 6 degrees, not because they are short path, but because they're short path despite having transitivity in the network. And yet there is one more thought that is the second and the true surprise. What we have talked about so far is so-called structural small worlds. It says that the median of the shortest search path are small numbers. Despite, so short search chains exist, despite triad closures, or more generally, despite transitivity. That's called structural. Okay, it does not talk about the functional properties. Remember all the way back to lecture 2 when we talked about structural properties based on the graph theoretic notion of a network versus functional models, which are the functionalities running on top of the graph. Right? For example, the hypertext connected web pages, that gives us the graph and the associated matrices, the structure. And then once we start adding things like a random navigation, then we are starting to model functionality, the functionality of web browsing behavior. And we, in the last two lectures, have also seen purely graph theoretic notions plus functionality based. For example, impose differential equation or dynamic systems on top of the graph. And in today's and the next lectures, we will indeed talk about the interactions, both positive and negative ones, between structural and the functional properties of a network. In particular, in today's case, we have just talked about the structural small world, but there's something more, something much more, which is algorithmic small worlds. That's the true surprise. What is algorithmic small worlds? Now remember, in Milgram's example, he wasn't just trying to find out the existence of short path. He's saying that these short paths can be discovered by very limited local information. Right, you are standing in the path here, and you really have no idea what the overall social network look like. So you have to decide which among your friends you are going to forward this letter to. Okay, friends are the people that you know by first name. You will look at the final destination. The name probably tell you something. It probably tells you the sex and even the ethnicity of the destination. The occupation also tells you something. For example, in Milgram's case, it's a stockbroker. So you may think maybe a banker is close enough to this occupation. I'll try to look for my banker friends, okay, as opposed to, say, a nurse. And of course, the physical address also tells you something. You probably want to forward to somebody closer to Boston rather than going out to the west to Los Angeles, for example. In other words, when you are deciding which one to forward to, you are solving some local optimization based on certain metric, and you picked one, let's say, with the highest likelihood of getting closer to the destination. And there are two issues here. One is what metric to use. We just mentioned three of them. Probably it will be a composite metric, some combination of all of them, okay, with different weights in your mind. And second question is, should I pick the one which has perhaps the best composite score towards this destination? If so, then that's called the greedy social search. There are other alternatives. For example, I may say, you know what, I'll just pick the friend of mine who is the most popular person. So even though I may not know this person, I trust this one have so many friends that she may actually know this person. If we follow that one, we'll soon reach a hub of the network connectivity. But in most models of algorithmic small world, people assume that participants follow a greedy strategy. Okay, first come up with a composite score based on these metric distances. Some are easy, like address, physical distance. Some are very difficult, like occupational distances. But whatever you use to quantify, come up with a composite score, then follow the greedy method to forward the letter. All right, now you got a routing algorithm, actually. Later in lecture 13, we'll talk about routing algorithms for machines to follow in the IP, the Internet Protocol. But in the social network story today, this is a greedy routing algorithm. You have limited information, only locally available to yourself, and then you make a local greedy decision. You can see this is a pretty suboptimal likely way to do the forwarding, and yet you can still find a short chain. So it is the discoverability of some short chain, may not be the shortest chain, but a reasonably short chain that is truly amazing. Not just the existence, there is a short path, but also some short path, whether that one or a close enough approximation, can be discovered by local interactions, by local decisions. That is what we call algorithmic small world. Fix a routing strategy like this greedy one, and yet you can discover short path. How can we reverse engineer that phenomena which was observed in Milgram's example? That would be the second task. So first task, second task for the rest of this lecture.